Welcome everyone! This week is going to be a bit lighter as far as videos go, and this is going to be compensated by the fact that there's more than usual to read and study on your own. This is given by the fact that in the videos I'm going through theory that allows you to build up Fourier series very strongly, and that is what you're going to be studying about on your own. Just as a setting ourselves in time, next week is going to be dedicated to Fourier transforms, and it's going to be the last week before the second review week. So this is just a setting. Let's delve into the topics. At first I'm going to look a little bit back and talk about generalized Sturm-Liouville problems. But first let's start with normality of eigenfunctions. This is in particular because there was a mistake in the previous videos, so I'd like to go through it a little bit more slowly. So we go back to the Sturm-Liouville problem that we have seen a bunch of times. Second derivative of y plus lambda y equals to 0 with 0 boundary conditions at 0 and at L. Then we have found the eigenfunctions of this problem being the sine of n pi over L times x, with n a natural number. If we want to rescale these eigenfunctions in order to have them being normal, so that means of norm 1, what we do is taking the inner product of one eigenfunction by itself and compute this integral explicitly. So this would be the sine of n pi over Lx multiplied by itself and the integral from 0 to L. So we can do a rescaling of our constant x. We introduce a constant y that is n pi over L times x. So our integral is now going from 0 to n pi. We have the sine of y times itself times L over n pi dy. So we can take L over n pi out of the integral. Now we have an integral without a constant of sin squared. There are two things we can use to solve this integral that we want to combine. The first is that sin squared plus cos squared is equal to 1 for any point, and the cos is a shift on the sin, the sine. We can also use the periodicity over 0 to pi. All of this can help us determine the fact that this integral is really the integral of sin squared from 0 to a multiple of pi at the multiple of pi divided by 2. So we see that our constant L over n pi simplifies with the n pi over 2 that we have, leaving us with L over 2. That means that the square of the norm of the eigenfunction that we have chosen is L over 2. In order to rescale it, we need to rescale the eigenfunction by a constant kn. This is a weight that is 1 over the thing that we have just computed. Just pointing out, it's not always possible to normalize eigenfunctions. The integrals can be either very hard to compute or just impossible to compute analytically. In this case, we just introduced the weight and we just defined the weight to be 1 over the inner product of the eigenfunction by itself, and there is a square root missing in here. Let's get to the generalized Sturm-Liouville problem. So the generalized Sturm-Liouville problem is when the weight, that is the W that is multiplied by lambda and y in our Sturm-Liouville problem, is not constantly equal to 1. So the weight can actually take positive values. And everything else is the same. The adjoint operator, self-adjoint operator H, that goes from the space of functions on A, B with boundary condition to the same space of functions on AB with boundary conditions. If we want to define it as the operator that satisfied the standard eigenvalue problem, so hy equals lambda y, then we have to define it as 1 over wx times the part that we had already. Why is this useful? So last week we have seen that we can just define it as minus parenthesis p times y prime, all of it prime, minus q times y. Why do we need to divide everything by w? Well, the reason is because solving hy equals lambda y, it's much easier than solving hy equals lambda wy. So we can either define h as 1 over wx times what we had before, and the inner product as the integral of the product of f, g, and w. And in this case, we have a standard eigenvalue problem to solve, that is hy equals lambda y, or we can define h as we did last week, but then we have to deal with the fact that our eigenvalue problem is generalized. That means that we have to look at hy equals lambda wy. And usually it's very hard to solve things in this form. That's why this week we're going to be looking at the generalized self-adjoint operator in which we have been dividing by w. This is possible because w has to satisfy the request that it's always strictly positive. So w cannot be 0. It can also never be negative, so there is never going to be a shift in signs. So the introduction of the generalized eigenvalue problem is interesting per se, but it's usually not what we want to be solving. We usually want to be solving the generalized self-adjoint operator in which we are dividing by w.